Are there questions from the last few lectures? All right. Today I'm going to talk about mock modular forms, and they first appeared in 1920, I believe. The story of Ramanujan is a very romantic and tragic story, which I'm not going to tell you in great detail. I think there's actually a movie coming out sometime in the next year about his life. But he went to Cambridge, where he worked with Harvey and did some beautiful mathematics, but he was a vegetarian, and the food didn't agree with him, and the climate didn't agree with him, and he came down with some illness. Eventually went back to India and died a couple of years later. But during the last year of his life, he was working hard. And I think a month or two before he died, he wrote a letter to Harvey. And in this letter, which you can actually find the letter if you ever go to Cambridge, not Cambridge in the US, but the real Cambridge, England, and you go to the Wren Library, they have a box full of papers of Ramanujan's, and this letter is in this box. And if you know somebody in the right college, they can get you in to do that. And he introduced things that he called mock theta functions. And mock is in the sense of like in Alice in Wonderland, there's a mock turtle soup. I think it's not, so mock means not quite real, but there's something kind of fake about it. So these were like theta functions to him, but they didn't have all the right properties of theta functions, so he called them mock theta functions. And he didn't really, as was his habit, he didn't explain what he was doing or define what he was doing or prove anything. He just wrote down formulas. So one of the formulas that he wrote down looks like this. So some infinite sum a series in a variable q and he also, I think he wrote down something like 17 of these things altogether. I'll just write down 2 of them. So he said that these are order 3 mock theta functions. And then he wrote down some other ones that he said were order 7 and order 5 or whatever. But he didn't define what the order was. And you can notice that these things are going to have singularities. Like we found when we looked at 1 over the eta function. So when q or q cubed or q to an odd power is equal to 1, or when q or q squared is equal to -1, so again at some rational values of tau, these things are going to have singularities. But after this letter, it was really very mysterious what these things were, what their significance was, what you're supposed to do with them. And a number of mathematicians worked on them. So for example, Watson, who I think is the same Watson of this famous book by Watson and Whittaker on mathematical physics. Andrews, who's a number theorist. Freeman Dyson, who's a physicist, but also has a serious interest in number theory and mathematics, and a few others tried to puzzle out what properties of these things were, but they really struggled to find a uniform description. And one of the main mysteries in their work was the question of what kind of modular properties do these have? And so in particular, if we say looked at that f of q, and we think of q as being e to the 2 pi I tau, so you could think of it as f of tau, then what's f of minus 1 over tau? Well, I'm not sure about this particular example, but you could find a kind of modular transformation property. I think Watson first found this. I'm not going to write down the details, but he found that it transformed sort of like a modular object, but then there was some weird integral here. And so it's not really modular, there's some strange thing going on there. And it took about 80 years before any real progress was made in figuring out how these things fit in to the general theory of modular forms. And I think it's fair to say that probably we don't have the best understanding yet. There's a lot of work being done on this. Yeah.
Is the discussion still about these particular 17 functions?
No, there's a much broader class of objects that are now, there's a much more uniform way of constructing Mach modular forms and understanding the properties, which goes beyond that list of 17 that were provided by Ramanujan.
You mean today?
Today, yeah.
But when these guys started looking into it?
When these guys started looking into it, I think they were mainly trying to understand the examples given by Ramanujan, but I think in a few of these papers they generalized some of his constructions and found some other things that they called Mach theta functions. So I think there were a few other examples. There's also another, part of this, it's really a kind of an amazing story. There's another part of this story, which is when Ramanujan died, he had, 100 loose leaf pages of all the results that he'd gotten during the last year of his life that hadn't been written up and hadn't been published. And when he died, they went to his widow, and then his widow gave them to some friend of his, I forget his name, but some Indian academic institution. He then sent them to Harvey because he figured out that Harvey would be the one who would most appreciate them and be able to do something with them. Harvey somehow lost interest in them, and eventually they went to, I think, Watson, and then Watson died, and then someone else got them, and then someone else died, and then they had this big pile of papers, and someone rummaged through them and found these. Anyway, after a long series of whatever, these pages ended up in the Wren Library, but the mathematical world didn't know that they existed. I mean, they just lost track of it in this whole chain of events. And then George Andrews was visiting Cambridge and asking somebody about a problem, and they said, oh, you should go look in the papers of Whittaker, or whoever it was. So he went and looked in these papers, and he recognized that there were all these pages that were not Whittaker's, but were Ramanujan's. And so in 1988 or something like that, there was a big, flurry in the math world that this lost notebook called the Lost Notebook of Ramanujan had been found. And he, in that notebook, had a bunch of results on Mach theta functions. And that also kind of revitalized interest in it. And I think he also had some new Mach theta functions in that set of papers. So there's this whole story about the lost notebook, although the librarians at the Wren Library don't like this because they say, it was not lost, we knew exactly where it was the whole time. But it was kind of lost to the math world, sort of like somebody finding, another symphony of Beethoven or something. So anyway, but there are more of them, Okay, so just a little bit more on the history. So the current point of view of these things really started in a PhD thesis of Sander Zwegers, who was a PhD student of Don Zagier, and in a 2005 paper by Brunier and Funke, which provided a connection of them to things called harmonic mass forms, which I will define for you. And since that time, they've played an increasing role in mathematics and now in some physics, string theory computations involving black holes. And they're a very active area of research, although, I don't know, it's still sort of, compared to modular forms, even though there's a more universal theory, it's still complicated to deal with them. I mean, I don't know, I don't think we have the best understanding yet, but it's greatly improved. Okay, so mock modular forms are essentially this, Mach theta functions are a particular example of Mach modular forms. So I'm going to discuss the general object. And this definition incorporates and generalizes the examples found by Ramanujan. So recall from our earlier discussions that on the upper half plane H, we can put a constant negative curvature metric ds squared is dx squared plus dy squared over y squared. We've generally been using tau for a coordinate on the upper half plane, so I'm writing tau as x plus iy here in terms of real and imaginary parts. And the group SL2R, acting by fractional linear transformations, acts as isometries. And there's a Laplacian, which is SL2R invariant. So there's also a generalization of this Laplacian, delta k, and there are slightly different definitions of this object given in the literature, but the one that I will use is that it's y to the 2 minus k d by d tau y to the k d by d tau bar. And you can show that delta k takes objects that are not necessarily holomorphic, but that transform in the same way as a weight k modular form. To weight k modular objects. So in other words, if you act on something that transforms like a modular form of weight k, even if it's not holomorphic, with this operator, you can just check by a direct calculation that you get something that again transforms like a weight k modular form. So a mass form, or Moss form, I'm not quite sure how it's pronounced, it's the name of a mathematician, is a function on the upper half plane I'm not going to go into quite a full detail. There's some growth condition at the cusps, which just is the sort of thing that we've seen before, but that transforms in the following way. Under modular transformations, where this is some multiplier system. So I haven't said that it's holomorphic. In general, it's not holomorphic. So maybe I should not necessarily holomorphic. Such that this weight k hyperbolic Laplacian acting on f gives f back again up to some eigenvalue lambda. So that's what a harmonic mass form is. Sorry, that's what a mass form is, a weak mass form. And there's a definition which is somewhat formal, not constructive, of what a Mach modular form is in terms of a special case of this. And so that's why I've introduced this concept, and I'll tell you what the definition, the sort of abstract definition of a Mach modular form is. And then we'll see a few examples that illustrate that, but I'm not going to be able to systematically derive any kind of general results. Okay. Just to be absolutely clear, I guess, in the definition of this, I should have told you that d by d tau is 1/2 d by dx minus I d by dy, and that d by d tau bar is given by that. Okay, so in this setup, if lambda is equal to 0, then f is a weight k harmonic mass form. So harmonic just meaning that it's an eigenfunction of the Laplacian, this weight k Laplacian, with 0 eigenvalue. All right, so now we're going to define some spaces of various kinds of modular objects and some maps between the spaces, and the definition of Mach modular forms will follow from this set of definitions. All right, so I'm first of all going to introduce something I'm going to call M hat sub k. This is the space of harmonic technical condition about growth at cusps, weak mass form of weight k. So this is the space of objects that I just defined over here. They transform like this under modular transformations, and they're eigenfunctions of this weight k Laplacian with eigenvalue 0. Mk with a little exclamation point up here is going to be the space of weakly holomorphic modular forms of weight k. So recall these are modular forms that are holomorphic except as tau goes to I infinity, where you're allowed to have, you know, some negative powers of q in the expansion, but they're holomorphic in the interior of the upper half plane. Now, it's clear that any weakly holomorphic modular form of weight k is an element of this space of harmonic mass forms of weight k because the weight k Laplacian has a d by d tau bar in it on the far right. And elements here are holomorphic, so this, well, except at the cusp at infinity, so this derivative will kill them and put us in this space. So we have a map between these two spaces just by inclusion. Now we'll define another map. So given a function f hat that's in this space of harmonic mass forms, I'll define a map S of f to be y to the k times df by d tau bar. So I claim that S of f is a weakly anti-holomorphic modular form of weight 2 minus k. So to establish that, there are two things we need to check. So first of all, I claim it's clear that this is anti-holomorphic. So by anti-holomorphic, what I mean is d by d tau of it is 0. And we know that the weight k Laplacian on f is 0, and this is y to the 2 minus k d by d tau y to the k d by d tau bar of f, but that's y to the 2 minus k times d by d tau of s of f, and therefore d by d tau s of f is equal to 0. So we now, okay, and then the other thing is that you need to check that S of f has weight 2 minus k, and yes, you guessed it, I'm leaving that as an exercise. It's not hard because you know how the imaginary part of tau, that is y, transforms under modular transformations, and you just have derivatives here, so it's not a hard exercise to check that. So that means we also have a map, which I'll call S, given by this, which is known as the shadow map, which maps this space of weight k harmonic mass forms to a space that I'll call weight m2 minus k, bang, with a bar. So the bar means anti-holomorphic. Now, this looks pretty, I don't know, formal, but I'll get to a punchline in just a minute and then we'll talk about it. So there's a theorem due to Brunier and Funke that this is an exact sequence, meaning that the whatever it is, the kernel of one map is the image of the preceding map, and the hard part here is to show that that for every element in this space of weakly anti-holomorphic forms of weight minus 2k, that there is some element, I don't know, let's call it f, or f hat, that maps to that element. And that's the hard part of their theorem, and I'm not going to prove it. Now, all right, so what in the world does this have to do with Mach modular forms? Well, you can use this theorem of theirs to construct certain objects which are going to be the Mach modular forms of Ramanujan and generalizations of it. And the simplest example of this involves a slight assumption, which is not the most general case, but is often true. So suppose we have a function which is anti-holomorphic and weight k. So a g of tau bar, which is a weakly holomorphic weight 2 minus k form. And is a cusp form. Vanishing as tau bar goes to minus I infinity. Sorry?
I just want to see, so the theorem says forever H there is no type.
Right.
I was just confused by the need to.
Well, Brunier and Funke prove, yeah, so that's the hard part of the proof. I mean, we have explicit, definitions of these maps, and it's clear that the maps do what they're supposed to do, but it's not clear that every element in here comes from something in here. All right, so if we have something that's anti-holomorphic in a cusp form, which is often the case in many of the concrete examples, not in every example, but in many. We can invert the shadow map explicitly just by doing an integral. So what that means is that we want to find a function which unfortunately is called G star in the literature. This G star is not the complex conjugate, which is what most physicists would assume. It's just a symbol to denote a function. Such that the shadow map acting on it is G of tau bar. So it's called G star simply because given a G, it's the thing that this shadow map acts on to give G. And we can simply integrate this equation to find that G star is equal to, there's some numerical factors here, which I hope I got right, but anyway, an integral from minus tau to minus I infinity, G of minus Z bar over Z plus tau bar to the K dz. So you can just check that this derivative times y to the k on this gives the function G of tau bar. All right, so now, finally, let me explain what this has to do with Mach modular forms. So, given a weight k harmonic mass form such that the shadow map acting on it gives a function G of tau bar, we can define a function f to be the difference between f hat and G star, which was the inverse of the shadow map. So f hat and G star live in this space of harmonic mass forms. But so when I take G, I go back to a G star, and then I subtract that from my original guy. And the interesting thing about this construction is that this is the object, which is a Mach modular form of weight k. So F, first of all, is holomorphic, even though F hat is not. And that's a simple calculation. We compute d by d tau bar of F. That's d by d tau bar of F hat minus d by d tau bar of this object I'm calling G star. But that's 1 over y times the shadow map on F hat, and this is 1 over y to the k times G. But G is the shadow of F, so that's equal to 0. All right, so this is a lot of formalism. The sort of main point of all this is that you have an object F hat. This function is modular, meaning it transforms like a weight k modular form. But it is not holomorphic. F is holomorphic but it's not quite modular because there's a modular transformation of F hat, but then you have to look at the modular transformation of G star, and it transforms in a more complicated way. So what Mach modular forms have to do with is a tension between having a function which is holomorphic and having a function which is modular. And there are situations in both mathematics and physics where you can't reconcile this kind of tension between holomorphy and Mach modularity. Yeah. G is, I guess G was anti-holomorphic, so. Yeah. And situations like this occur in physical settings. For example, they often occur in the analysis of supersymmetric theories, where supersymmetry often requires certain terms in the effective action to be holomorphic functions of fields. But if you try to integrate out some massless fields in the theory and get some kind of effective action, you'll often find that it's not holomorphic. So there can be a tension, which is called the holomorphic anomaly, in the formulation of the effective action for supersymmetric gauge theories. And there are other examples of computations, basically in situations where you have a discrete spectrum and a continuous spectrum, where computing certain kinds of things like the Witten index, the continuous part of the spectrum can destroy holomorphy. So this is actually a situation, a general situation which occurs in physics and mathematics, and its particular implementation here is what defines Mach modular forms. I should give you a word of caution, which is that much of the literature on this defines the shadow map differently than I did. They often define the shadow map to be take this derivative but then complex conjugate the whole thing, so that the shadow map maps you not to anti-holomorphic modular forms of weight 2 minus k, but to holomorphic modular forms. And this definition makes certain formulas more complicated, and I think the only reason that people do that is because they're so used to dealing with holomorphic modular forms that they don't really like to write down formulas involving anti-holomorphic modular forms. But I think that's kind of a weird bias. So anyway, if you try to compare what I've done to things in the literature, you should be aware of that I am using a slightly non-standard definition of the shadow map, which I thought made things slightly less complicated. But okay, so this is kind of the abstract definition but it is not constructive unless you have a way, an explicit way of constructing these harmonic mass forms. So I want to give you a couple of examples. And unfortunately, the examples that I can give you, that I can fairly easily work out explicitly that they're Mach modular forms, are not that interesting. And then there are examples that are of more recent interest and non-trivial, but actually proving that they satisfy all these properties is quite a non-trivial exercise, and I'd hoped to do it, but there's no way in the time available, so I'll have to refer you to the literature if you really want to go into the details. All right, so the first example is really trivial. Just take a holomorphic modular form of weight k, and that is a Mach modular form by this definition. Now, I should say something. There's another way of, well, sometimes people define Mach modular forms in a slightly different way. So what they involve really is a pair. F is a Mach modular form. G is a function called its shadow, which is a weight 2 minus k honest modular form. So, and these are the same F and G's that I wrote down in that earlier formula, related by G, or, well, anti-holomorphic or holomorphic, depending on which definition you make. So I made it anti-holomorphic. So this, just an ordinary holomorphic modular form, example J of tau, is by this definition a weight 0 Mach modular form with a vanishing shadow. So according to this definition, Mach modular forms are a generalization of modular forms that include ordinary modular forms. And I don't think this is, well, it's sort of vacuous, but I don't think it's really vacuous. And the reason I don't think it's really vacuous is, if we think, say, of J of tau, it's not the reason that it's honestly modular rather than mock modular is because since J has weight 0, its shadow would have to have weight 2, but there are no weight 2 modular forms, holomorphic or anti-holomorphic. So in other words, I would like to encourage you to think that everything is a mock modular form. Every modular form, not everything in the world, but sometimes it's modular because there aren't any possible shadows. And so when the space of shadows vanishes, things that are mock modular turn out to just be honest modular forms. And that's going to be a useful point of view. I mean, we often find things where we'd like something to be true, but there's some obstruction to it being true. But when the space of obstructions is empty, then it's true. And so we would like something to be modular, but there's this space of obstructions, which is the space of shadows. And if there are possible shadows, then generically we'll get something that's not modular but mock modular. But in special cases, the space of shadows vanishes and we get something honestly modular. All right, so that's the first example. Really trivial, but at least, I don't know, it shows you that there are such things. The second example is also kind of trivial and well known under a different terminology, but it's worth pointing out. So recall that we defined Eisenstein series E2k for 2k equals 4, 6, 8, etc. And these provided our first examples of modular forms. They were given by 1 with weight 2k over the modular group, and they were also related to these functions that we called G2k. And G2k, remember, was equal to a sum and an m integer not equal to 0, 0 of 1 over n tau plus m to the 2k, which maybe I'll just write as sum prime 1 over n tau plus m to the 2k. Now, when I did the analysis of the modular properties of these guys, so demonstrating the modular properties involved reordering terms in the sum, and that was allowed because for those values of k, the sums were absolutely convergent. But there is a, you can make sense of G2 for which the sum is not absolutely convergent, but because it's not absolutely convergent, you're not allowed to reorder terms in the sum, and as a result, you find a slight deviation from something that's modular. So this is something that occurs in various places, and so I'm going to go through a little bit of a calculation, and after I do that calculation, then I'll give you a break. Okay, so one way of doing this, which I don't know, it kind of looks like the sort of thing a physicist would do, but I actually found this in a lecture of Don Zagier, is to consider the following object, G2 epsilon of tau. Epsilon is meant to be some small quantity. All right, let me just write this as some prime. I defined some prime there, some on M and N. M and N not both equal to 0. 1 over m tau plus n squared times the absolute value of m tau plus n to the 2 epsilon. So epsilon is some small positive quantity. Now, once I do that, this sum converges absolutely for any finite epsilon. And so we can now proceed. So the previous reordering of terms calculation, which I'm not going to do, but it's completely straightforward, shows that under modular transformations, this quantity transforms like this. So this would be a weight 2 part, but because I've put the absolute value of m tau plus n here, you get a factor that involves the absolute value of c tau plus d, and that follows just by, well, you can do it, say, for tau goes to tau plus 1 and tau goes to minus 1 over tau, which generate SL2Z. Do it for those two cases by the reordering we did, and you'll find that this is what you get. All right, now you do a little trick, the idea being to try to subtract something off of this which will cancel the lack of absolute convergence of the sum as epsilon goes to 0. So you define the following integral. I epsilon of tau is the integral from infinity to infinity dt for z plus t squared times the absolute magnitude of z plus t to the 2 epsilon. Note the similarity to the denominator in G2. And consider G2 epsilon minus twice the sum from m equals 1 to infinity I epsilon of m tau. No, this is t. Z, I guess. Z. Sorry. Maybe I'll make everything a tau. Since I'm using okay. Okay, so this is equal to twice the sum n equals 1 to infinity, 1 over n to the 2 plus 2 epsilon, This comes from the m equals 0 term in G2 epsilon. And, okay. Plus a sum m equals 1 to infinity, a sum n equals minus infinity to plus infinity of 2 over m tau plus n squared, m tau plus n to the 2 epsilon, minus twice the integral from n to n plus 1 dt over m tau plus t squared, m tau plus t to the 2 epsilon. So this term comes from all the m not equal to 0 terms in G2 epsilon. And this term is that sum on the integrals using the fact that if I sum on all integers n, the integral from n to n plus 1, that's the same as the integral from minus infinity to plus infinity. So we've taken this integral from minus infinity to plus infinity in I epsilon, summed over all m's from 1 to infinity, and written it like this. So now, this, in the curly brackets, is perfectly well defined as epsilon goes to 0, essentially by the integral test for sums. This behavior is canceling off the bad behavior of this when epsilon goes to 0. So we get something that's absolutely convergent by having subtracted off this integral, and we can now just set epsilon equal to 0 to evaluate it. So the last term on the right-hand side of this equation, that is this, can simply be evaluated. So it is, after doing the integral, and putting epsilon equal to 0, it's equal to 2, the sum from m equals 1 to infinity, the sum from n equals minus infinity to plus infinity of 1 over m tau plus n plus 1 minus 1 over m tau plus n. This sum is what's called a telescoping sum, and it telescopes to 0. So what do I mean by that? I mean if you have a sum from n equals minus n to plus n of the form a n plus 1 minus a n, that by writing down successive terms and canceling terms off, you can see that this is minus a minus n plus a n plus 1. And in our case, these a n's are these quantities 1 over m tau plus n. And if a n goes to 0 as n goes to infinity, then this whole sum goes to 0, and that's what's happening here. The whole sum telescopes to 0. Okay, so what that means is that if we define g hat 2 of tau to be the limit as epsilon goes to 0, g2 epsilon of tau, this is equal to g2 of tau plus the limit as epsilon goes to 0 of 2 times the sum from m equals 1 to infinity of I epsilon of m tau, where g2 of tau is now defined in terms of this particular ordering of the sum. So we have a situation here where g2 of tau is holomorphic, but it's g2 hat of tau that transforms like a weight 2 modular form, because it transformed like that for finite epsilon, and then we took epsilon goes to 0. And to connect the two things, you have to do one more calculation, which I will leave as an exercise, which is to show that the limit as epsilon goes to 0 of the sum of m equals 1 to infinity of I epsilon of m tau is simply minus pi over 2 m tau. So the final answer is very simple. g2 hat of tau is g2 of tau minus pi over m tau. This quantity is holomorphic. This quantity is not holomorphic because of the m tau here, but it transforms like a weight 2 modular form. And we can check that if we take the weight 2 Laplacian acting on g2 hat, that's d by d tau y squared d by d tau bar of g2 hat. Well, that's d by d tau y squared. D by d tau bar has an I over 2 d by dy, and the imaginary part of tau is 1 over y. So you can see that this gives a 1 over y squared, and then I have d by d tau of y squared times 1 over y squared, so that's equal to 0. So g2 hat is a weight 2 harmonic mass form. And the shadow of G2 hat is y squared d by d tau bar of G2 hat, but that's just equal to I pi over 2 if you carry out the differentiation. And it's a constant. Well, a constant is a weight 0 modular form. So this example shows that all the pieces fit together correctly. G2 of tau can be thought of as a Mach modular form of weight 2. The shadow is a constant. It's holomorphic, but it's not quite modular. Its lack of modularity is made up by the modular transformation of this bit that you have to add. And the difference is transforms like a weight 2 modular form, but it's not holomorphic. G2, or its cousin E2, are usually called quasi-modular forms. And this modular transformation property was known and understood well before the recent interest in Mach modular forms. And if it were just for this example, this whole formalism of Mach modular forms would never be invented. This is too trivial a case. So the only two examples we've talked about either have zero shadow or a constant shadow. The really interesting cases are when the shadow is some non-trivial modular form, but these are the cases that I can most easily illustrate the formalism with. So that's why I went through the details of this. All right, this has been, I've gone on for a long time, so let me give you a break and let's reconvene at 25 after. So and I believe the coffee machine works. So that's something. All right. So if I had, I don't know, another 10 hours and you had, a lot of more patience, what I would do is try to give you some details of the construction of other kinds of less trivial Mach modular forms and their applications. But I don't really have time to do that. So I'm just going to say a few words, summarize a few things, and encourage you to go to some of the literature if you want. So in Swager's PhD thesis, he gave 3 constructions of Mach modular forms. The first was in terms of some quantities, some sums, which are called Appel-Lurk sums. I'm not going to write them down for you, but they are related to characters of the n equals 4 superconformal algebra. And these characters are important ingredient in analyzing string theory on the K3 manifold, because string propagation on K3 has an n equals 4 superconformal algebra. So that's one, sort of the first physics connection. He then gave a construction in terms of meromorphic Jacobi forms. So meromorphic Jacobi forms are functions of z and tau with the modular and elliptic transformation properties that we discussed earlier when we discussed Jacobi forms, but they're allowed to have poles in the variable z. And he showed that when you have such meromorphic Jacobi forms, there's a way of extracting a Mach modular form from them. And then the third construction that he gave was in terms of theta functions associated to lattices, but where the signature of the quadratic form that defines the inner product is not positive definite, but rather has one negative eigenvalue. So again, I'm not going to give you the details, but you have some lattice, but now think of this lattice as a lattice of, say, space-time points in 1+1 dimension. So some points are space-like, some points are time-like, some points might be null. And if you try to define a theta function for such a lattice as a sum over lattice points, q to the v squared over 2, this sum diverges because you can have points that have both positive and negative length squared, and so this sum diverges like crazy. But what he showed is that you could, in some cases, modify this to something which is not holomorphic anymore by putting in a convergence factor, which depends on tau and tau bar, and also depends on two vectors C1 and C2, which basically define a cone, and you sum over the cone in defining this lattice theta function. So I'm not going to give the details of this either, but he has these three different constructions, and he uses all of them, and sometimes there are Mach modular forms which can be formulated in any of these three different ways. Now, the second example, perfect Jacobi forms, shows up, or has shown up in two places recently. So the first is in the counting of black hole states in 2D string theory on K3 times T2. And it's also shown up in a new kind of moonshine called umbral moonshine. So this is due to a number of people, but it was explained in great detail and with a lot of sort of in the most complete way in a very nice paper to be a book, I think, by Dabelkar, Murthy, and Zagier. And umbral moonshine started out with a short paper by Eguchi, Oguri, and Tachikawa, and then was extended by Miranda Cheng, John Duncan, and myself. So I want to just say a few words about these two applications, and I think I may end a little bit early and just give, see if there are questions or things that you would like me to say a little bit more about so that you have more of a chance for questions. So this is very sketchy, but in the problem of counting black holes, there is a certain counting function more chalk. And I'm not defining this, but I'll just tell you that it has an expansion in one of the variables, which involves a set of weight minus 10 index m weak Jacobi forms with a double pole that is going like 1 over z squared as the elliptic variable z of the Jacobi form goes to 0. And by slightly generalizing Zweger's analysis, what Dabelkar, Worthy, and Zagier showed is that you could always take these, and there was a kind of canonical decomposition into a term that has this double pole, still has good elliptic properties, and is related to these Appel-Lorentz sums, and that the remainder is something called a mock Jacobi form. And this mock Jacobi form has an expansion of the type that we wrote down for usual Jacobi forms. But for a usual Jacobi form, we said that this quantity was a vector-valued modular form, but it turns out here it's a vector-valued mock modular form. And I obviously haven't proved anything or even given you the details, but their discussion is extremely constructive. That is, they tell you exactly what these Jacobi forms are in terms of known modular functions, theta functions. They tell you exactly what's involved in doing this decomposition, and so you can use their prescription to generate infinite families of mock modular forms, which are these quantities HR. And the motivation for doing this came in trying to resolve a physics puzzle. And the physics puzzle was the one that I mentioned last time, in that when you look at the actual black hole solutions, it turns out that you have black holes that have some net charge Q, which are single center. And then you also can have solutions with the same charge, but which have double centers, and you would like to exclude these in the counting. It turns out that the single center black holes are counted by the coefficients of this quantity psi mf of z and tau, this mock Jacobi form. So there's a mathematical construction in terms of vector-valued mock modular forms, and there's a physical interpretation which is that if you want to compute the degeneracy of these black holes, if you want to compute their entropy, and you want to just focus on the single center ones, then they are counted not by a Jacobi form, but by a Mach Jacobi form. And so here, if you want to get a modular answer, you need to add both the single center and the double center ones. If you want to get an answer which is holomorphic, you just do the single center ones, but it's not modular. So again, there's sort of a physical interpretation of the tension between holomorphy and modularity, but here the physical interpretation is whether you include or don't include these double center black hole solutions in the gravity description of what's going on. And the moonshine connection was a very close variant of this. So in this work with Chang and Duncan, following Eguchi, Oguri, Tachikawa, and DMZ, we considered Jacobi forms with a first order pole at z equals 0, and with the slowest possible growth of the coefficients. The growth of the coefficients can be characterized in terms of a condition So again, you get some vector valued Mach modular forms, and the growth condition turns out to be that q to the 1 over 4m hr of tau is order 1 as tau goes to I infinity for all r. So you have to do something that's like the Hardy-Ramanujan estimate of the growth of the number of partitions, but there's a variant of that that applies to Mach modular forms. And you can show that if this condition is satisfied, then the coefficients of this Mach modular form grow as slowly as possible, consistent with its weight, or weight and index. So again, this formalism of DMZ is completely constructive, and you can just start working out what these objects are. So if you start with the meromorphic form of index 2, then you find that you construct a single component Mach modular form, and you can work out its Q expansion. And it turns out that all of these coefficients, the first few anyway, are dimensions of irreducible representations of a sporadic group known as M24. So it's one of the sporadic finite simple groups. And this fact and a connection to the K3 elliptic genus is what was pointed out by Eguchi, Oguri, and Tachikawa. But it turns out it can be extended. And if you look at this same kind of analysis at m equals 3, for example, then you find a two-component Mach modular form. And this exhibits a kind of moonshine, that is connection to the representations for a group which is related to another one of the Matthew groups, a group called M12. It's another Matthew group. The notation 2 dot here means that this actual group has a Z2 normal subgroup, and the quotient by that Z2 normal subgroup is M12. So just by following math and working very hard, we were able to show that there were 23 examples of vector-valued Mach modular forms and groups, and for reasons that are not understood, these are labeled by Niemeyer lattices. Which were, as you may recall, the rank 24 even self-dual lattices. So there's quite an expansion of the moonshine story, and there's to me, a completely remarkable, strange thing going on, which is there are a set of mathematical tools which have been the subject of these lectures. Modular forms, Jacobi forms, Mach modular forms, things that we haven't been able to get into that are kind of a generalization of modular forms called Siegel forms, other ways of constructing them called Rademacher sums. So there's a whole, long list of technical, interesting, complicated mathematical tools. And these tools have been necessary to understand in complete detail the counting of black hole states. And they also exhibit some special versions of them, explain or provide some kind of moonshine that links special modular or Mach modular objects with some very special, often sporadic groups. And it's the same long list of mathematical techniques and topics that appear in both of these problems. Now, I know, and you'll tell me, that the same mathematical tools often occur in different areas, and the fact that you have the same math in two different areas doesn't mean that they're related. But the link is so close here, it's really, in terms of what I was just describing, it's whether you have double poles or single poles in some Jacobi form, but all these tools apply and are required for a full understanding of each of these. So it really, to me, suggests that there's a connection, but so far no one has been able to figure out exactly what that connection is, because the Mach modular forms, Jacobi forms, Siegel forms, blah, 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 that appear in the black hole counting are not quite those that appear in moonshine. They're a little bit different. But it really suggests to me that there's some kind of special string theory or conformal field theory-like thing, or space, or some kind of three-dimensional gravity, which is something that's a little different than what we've encountered so far, but that in that theory there will be some special kind of minimal entropy black holes which will be linked to the representation theory of really interesting sporadic groups. Whether that's actually true or not, I don't know, but it's a general topic that I think many people are interested in, because if it were true, it would really be quite remarkable. The counting of black holes really is a number theory problem. You're supposed to get an integer. for big black holes, of course, you know, but you really get an integer, and there are computations in string theory backgrounds or in supergravity that give complicated sums that turn out to be integers. So it's suggesting that there's a way of linking number theory, geometry, black holes, sporadic groups. I don't know. Anyway, to me, it's just it's very fascinating, but we don't necessarily know the right way to make progress. Do we pursue the math? Do we do the physics? Try to connect them? But it's what is kind of motivating my research over the last couple of years. And so I wanted to end by just kind of mentioning this connection and one of the reasons why I've spent all this time developing the math of modular forms, because I think it not only has many applications that we've seen already, but that it's going to be something that leads to new connections in the next 5 or 10 years. So I think I will end here, but I'm very happy to answer questions either of specific topics or just more general questions. Yeah. It's possible to construct, it's actually very easy to construct a string theory that has these kinds of groups, because you can just take the bosonic string on R24 mod one of the Niemeyer lattices, and it turns out that the groups that I talked about are related to the automorphism group of these Niemeyer lattices modulo something called the Weil group, generated by reflections in the roots. So if you do this construction, you will get a string theory that has this group G as a symmetry group. However, anything that I know how to compute in this theory, like the partition function, is modular. It's not Mach modular, and the representations of the groups that you get are not those that you get in umbral moonshine. So I don't know if that means you're supposed to start with this and then do something else to get something Mach modular, or whether this is not the right approach. I suspect it's not the right approach, but it's, yeah. Other questions?
So you talked about these 23 groups. You said that you had found that there are 23
Right.
groups.
Right.
Is that the number of sporadic groups?
No, and many of the groups that we found that are connected with these automorphism groups of Niemeyer lattices are very simple groups. In a few cases, they're trivial. Sometimes they're just Z2 or Z3, but they can be as big as M24. There are 26 sporadic groups, or 27, depending on how you count, but only a few of them are directly involved in umbral moonshine.
Isn't that suspicious that only some of them make it?
Many things are suspicious in this business, but the question is figuring out which suspicions are the right ones to follow up. I don't know whether, I mean, I would say so far the moonshine business does not seem to be a uniform way of understanding all sporadic groups. It does seem to be a way of understanding some sporadic groups, usually those that occur as subgroups of the monster. But I think of the 26 sporadic groups, there's something like 6 or 7 which are not subgroups of the monster. They're called the pariahs. And I don't know of any moonshine construction that really involves them in a deep way. So, yeah.
Mach modular form implies that the underlying theory is conformal.
Well, there's a purely mathematical definition that doesn't say anything about conformal.
Is it possible to get something non-conformal from the physics if you do that mathematics?
The one thing that some people have been exploring is to look at the elliptic genus of non-compact conformal field theories. One of the nicest examples that was analyzed by Iguchi and Sugawara and Troost and collaborators is string theory on what's sometimes called the cigar geometry. which is related to a coset like this. So this is not string theory on a compact manifold, but on a non-compact manifold. And because it's non-compact, just as in quantum mechanics that has, you know, both bound states and scattering states, you have a spectrum that can include some discrete states, but then there's also a continuum, and some of the discrete states can be in the continuum. And when you try to define the elliptic genus in a situation like this, summing over discrete states will give you something that's holomorphic, but to get something that's modular, you need to sum over the full spectrum of the theory. And you have to integrate over the continuous spectrum, and it turns out that supersymmetry does not quite make things cancel when you have a continuous spectrum. Boson and fermion states are still paired by supersymmetry, but there can be a difference in the spectral density of bosons and fermions, which gives a non-zero answer. So if you try to compute the elliptic genus in such situations, you get answers which reflect a kind of mock modularity, where there's a tension between modularity and having something that's holomorphic. But I don't know of an example like this that really directly gives you the mock modular forms of umber moonshine on the nose and explains what's going on. I mean, there's some relations, but I don't think there's a completely satisfactory story yet. But this is one way of trying to get something mock modular out of a conformal field theory, but one that has a non-compact target space. Anybody else? All right, well, thank you for your, I've really been impressed and pleased by the attention and the fact that you've kept me honest and asked good questions. So thank you very much for doing that.